Okay, we'll get started. Welcome everyone. This is session 1B, road design and speed management. Hopefully you're in the right session. My name is Jennifer Russell and I'll be your moderator for the session. There's a few housekeeping items that I'll quickly mention before we officially get started with the presentations. First off being that the conference interpretation will be a little late for this session. So please stand by for that if you do need interpretation. You can find the interpretation button at the bottom of the screen and select your preferred language. As I mentioned, they will be a little late for this session. Please use the Q&A tab at the bottom of the screen to submit any questions that you have for the presenters rather than the chat box. And we'll moderate the Q&A session after each presentation, so after each speaker. If we have time at the end and there's any questions we didn't get to, we'll be happy to try and get those answered before we wrap up. Throughout the conference, we encourage you to post to social media using the hashtag CARSPRI 2021. Any posts with that hashtag will also appear on the social wall in the lobby. And with that, we'll get started. I'll introduce you to our first speaker, who is Adam Shafee. And Adam, I'm going to pass the screen and the mic over to you.
Okay, thank you, Jennifer. And that should do it for share. Hopefully everyone can see and hear me okay. All right. So hopefully everyone is enjoying the event so far. Thank you very much for the opportunity for this discussion this afternoon, really regarding technology to assess the speed of vehicular traffic in our public roadways. So just a little bit of background before we get started. My organization is known as LED Roadway Lighting in Livable Cities. We have been manufacturing Canadian technology for road and area lighting since about 2007. And more recently, we are also manufacturing and designing communication systems for our street lighting and also sensor systems to attach to these street light systems. It's going to be the focus of today's presentation. Just as a little bit of where we are and what we've been, we are very focused on the Canadian market here and at home, but we also have our technology abroad in over 65 different countries around the world right now. And some of those technologies include street lights, as I mentioned, but also lighting control systems and increasingly some of the sensor technology, which I will discuss with you this afternoon. So a little bit about where we are going to go. This technology has been reviewed by a third-party organization, and they've done some assessments of typical technology that's out in the market to assess and report on vehicle speeds. So I'm going to do a little bit of a technology review on some of the legacy pieces that are typically used to measure these types of parameters, and then compare that to some of the new means of doing that with some technology that my organization is bringing to market that'll hopefully empower a lot of our public decision makers regarding what's happening on our public roadways. So why are we doing this? Well, it's no secret here at this particular event. We know that increased vehicle speeds in our public roadways is an increased risk factor for injury, serious injury, and fatality. So no new information there for this group, but there are multiple organizations around the world, WHO, BRAKE, others that we've heard about in the conference so far today that are interested in monitoring and working on speeds of vehicles in our public roadways for road safety. So what do we do when we get this data from the streets? Well, we really have an opportunity now to empower our municipal councils, our city councilors, our departments of transportation to really address speed in our roadways on a very specific basis. And the technology that I'll share with you and highlight today is a means to empower a lot of that data coming into these public officials so that we can take any one of a number of actions to help and improve the safety on our roads. So the new piece here is the fact that we can now acquire this data based off of the street lighting infrastructure itself. For those of you that aren't as familiar with roadway lighting technology, here's an example of a typical street light. That's an LED street light. And in North America and in a number of countries around the world, most of those street lights on our public roadways have a similar socket that you're seeing on the top of this particular one. That socket is a standardized interface that we can use traditionally to locate a photocell type sensor that'll turn the light on at dusk and off again when the sun rises at dawn in the morning. But that location is also an opportunity to deploy not just controllers for our public street lighting, but also a great vantage point to deploy sensors as well. And that application for measurement of vehicle speed is one that's really tuned to that particular location on the street light, because it is got a great view of the roadway happening underneath it. It's a little bit removed from the public landscape, and it's got a great accessibility to public traffic without interfering with the flow of that traffic to perform measurements. So how does that device become a roadway sensor for vehicle speed? Well, there's a sensor-ready device on the left side, moving to the right-hand side, where we've installed now a radar traffic sensor pod onto that common base, and then that device engages toollessly into a street light. So from there, the data is transported back over any one of a number of networks to the municipal level, or to the decision makers, or the law enforcement, whoever's deployed the technology. Typically, that data these days is flowing back over a cellular connection, so a public mobile network, for example. There are other networks available as well, but that's certainly the most common that we're hearing from in the market for these types of devices. And that gives us a lot of freedom for the location of these measurement type devices. We can really locate them on any street lighting asset where we have a mobile phone signal, which these days is practically anywhere in the environment. So as long as we have those two pieces, we can put these sensors out to measure and monitor traffic. We're no longer restricted to specific blocks and within our cities, specific pieces of infrastructure, or specific locations that we can deploy sensing technology for speed. And that data comes back over that network, it's received, and then the most important piece is that we get that data back out into the hands of those who are interested and can take action on it. Whether that is from a connection point between a cloud-hosted software into another traffic management software, for example, or that data comes out as a PDF report landing in the appropriate person's inbox once or twice per week or once a month, whatever the desired frequency is. And we envision that this system can connect to a lot of other smart mobility type systems, as we're increasingly interested in the number of vehicles, pedestrians, cyclists using our roadways, sharing that public road, active transport going forward. There's a lot of more inputs and outputs for these type of data from our city streets. So just to share with you a little bit of that review of what exists for this technology. Traditionally, pneumatic tubes such as these were used for a lot of these types of studies. We are a little bit restricted in what data we can capture and the duration on which we can capture it. So these devices typically have to be secured to a road sign or other fixed asset, so they can't be vandalized or removed or stolen. We can get vehicle speed and direction of travel. And typically this is done for a study that lasts only maybe about a week or 10 days on average. Very challenging to get systems longer than that without doing a lot of maintenance to change out battery packs, etc., or to maintain that equipment in the field for those short-term deployments. Also, vandalism of these assets is a challenge as well. In this country, we can't do a lot of traffic studies in the wintertime just due to regular road maintenance and snow clearing. So this is really a very short-term, short duration, and really a short window of time during the year when we can carry out the studies with this type of equipment. Video analytics are also available. This equipment, attaches to a pole, similar to this as you see on the screen. It consists of a camera and a data recorder, and the camera captures vehicle information and then processes that at the edge, producing count reports that are then accessible offline or over the web. These pieces of infrastructure are generally deployed at sort of pedestrian height. So they are, again, suspect to the vandalism. They also have battery packs as the other technology. So you're very limited, again, in the duration on which you can impart a traffic study to count your vehicles and speed. There's a cost model that's involved as well, and typically these are installed and run via consultants' reports. So they will get sort of these short duration snapshots, if you will, of what's happening at various roadways in our public landscape. Radar speed boards as well have become increasingly common in the last number of years, both these temporary installation trailers, as you see on the left side, or these more fixed installation that you see on the right-hand side of the screen. Some of these do have the ability to record vehicle speeds. Primarily, they're just used just to straight ahead warn the drivers that are approaching them of what their speeds actually are. There's been some question about the applicability of data, because typically these also modify the driver behavior, and they don't natively capture the speed that would be inherent on the road if these sort of flashy technologies are there warning people of what their behavior truly is. So there's some question about the applicability of data. Also, they are deployed, but they are generally deployed with solar panel or battery pack. So they do also have that limited time span on which we can capture information about vehicle speeds in our public roadways. Depending on where they're deployed and how, that could be challenging as well for the vandalism aspect and theft of infrastructure. So just to highlight again how this new approach is very radically different, these sensors for traffic are deployed on top of the streetlight. They are installed similar to a traditional photocell that our lighting crews will be very familiar with installing as an accessory onto our public lighting networks. There's a short aiming exercise of a few moments to aim the radar directly to the roadway where we are interested in capturing the data. And once that's performed, we've got power, usually 24/7 to that street light, as well as a permanent mobile data connection back over that cellular network, so we can begin to receive data almost immediately. These technologies are located high above the street, so they're almost inconspicuous to the average road user and driver. They don't know that traffic speeds are being monitored in a particular location. And it's those public lighting crews that have the knowledge and the expertise and can install these types of devices very rapidly. That location also makes them pretty safe from a vandal-resistant perspective as well. They are sort of blending in back into that public landscape and not introducing additional urban clutter, so folks don't know they're actually sitting there. So all of this begins to beg a broader discussion of something that's called microsensing. A lot of the communities that we're speaking with, and we know there's a lot of interest in the market for those wanting to monitor very specific zones within the municipality, either school zones, hospital zones, etc. Traditionally, that's very expensive to do with incumbent technologies. But when these types of sensors that we can attach readily to public street lighting, which is pervasive throughout our urban and our suburban environments, we really have the ability for the first time to monitor street and speeds on a very granular scale across a region. So we can identify target areas or known infraction areas, and then we can better target use of our policing, our law enforcement resources, or our municipal resources, where we try to tackle those speeding issues with infrastructure changes or modification to the public roadway. And some of the common users and consumers of this information are shown here. Again, technology that's meant to empower those who can make and take actions and help improve the safety of our roadways. Speed sensing is just one application of this technology. There are others that we can leverage from the streetlight as well, including air quality, acoustic sensing for noise, visual sensing coming a little bit later, but also other applications. We're talking about safety of the whole road, not just drivers. So we know that there are incidences where sometimes that infrastructure where public lighting is mounted on can become energized due to maintenance or issues with underground electrical service. Technology based in the streetlight can actually help us to detect those issues of live and energized assets before there are unfortunate incidents for our pedestrians and our sidewalk and other users in the roadway. So there's a lot of applications that we can take advantage of to improve the general safety of the traveling and the pedestrian public by taking advantage of those street lighting assets in new ways. So hopefully there's been some insights here for those of you in the audience, and I'd be happy to open up for a couple of questions in the few minutes we have left. Thank you.
Thanks so much, Adam. If anyone has any questions, please drop them in the Q&A box and we can make sure they get answered.
And if there are no questions that come in now or in the next couple of moments, we do have a virtual booth as part of the exhibit portion of the program. So feel free to stop by and see us at that point.
We did get a couple that came in. So do any of your products have an all-in-one radar, air quality, noise, etc.? So
right now, just due to the form factors, these are separate sensors. But the ubiquity of the street lighting devices in our public landscape means that we could monitor adjacent lights. So for example, we could monitor air quality on one light and speed of vehicles on the next light, or getting an idea of traffic congestion, or we could mount sensors concurrently on the same piece of infrastructure. So that's possible. I just see a second one there, Jennifer, about validating the data. So we do have benchmarks against conventional radar and technology, and that's something that we are continuing to work on and validate with our partners in the field. The studies we've performed to date indicate we have excellent correlation with existing technologies for monitoring speed.
Great, and we'll take one more question. So is the data live? Do they differentiate for pedestrian, cyclist, vehicle classification?
So for this technology, the data are monitored 24/7, and then they're periodically reported. It is very privacy aware. So this is a radar-based system that does not uniquely identify pedestrians, cyclists, or vehicles. It merely counts and measures the speed of those assets traveling underneath the radar.
Great, and I think that might have answered that fourth question that just came in as well around privacy concerns.
Okay.
Thanks so much, Adam.
Okay, thank you very much, everyone. Enjoy the conference.
And our next speaker is Alex Nolay. And so Alex, I will hand you the screen and the mic.
Okay. All right. I think we're good now. Okay, so thanks for the opportunity to present today. So I'll be talking to you about a legal case I was just recently involved in, which was about the construction of floating bus stops and a complaint filed by a group of people with reduced visibility, which indicated that the new bicycle facilities discriminated against them. So the decision made by the British Columbia Human Rights Tribunal is very interesting, and it will have impact on us, so road safety practitioners, not just in BC, but probably across the country. My presentation outlines, I'll introduce the project, some of the safety review or the safety results that came out of it, the hearing and court discussion or decision, the potential implication, and then questions. So the study area consisted of the 1.2 kilometer road section of Pandora Avenue in the city of Victoria in British Columbia. Pandora Avenue is an important commercial corridor in the city's downtown core. It was a one-way, two-lane street with on-street parking on both sides. It carried on average of over 10,000 vehicles per day. It's a frequent transit corridor. There are a number of buses running on it. Sidewalks were provided on both sides of Pandora, and there were 9 intersections, including 7 signalized and 2 unsignalized intersections. So the reconstruction of Pandora Avenue involved the installation of a two-way separated bicycle facility on the north side of the roadway. The bicycle facility is separated from the adjacent motor vehicle lanes by a combination of a raised concrete island and painted buffer strips with bollards. There are 5 mid-block marked crossings, pedestrian crossings, that are provided along the corridor, and the raised crosswalks are also provided at each transit stop, providing continuous routes from the sidewalk to the boarding platforms. So you can see an image on the left of a floating bus stop. So the definition is that there are transit stops where the boarding platform is separated from the sidewalk by a bicycle facility. So pedestrians would have the right of way once they enter the crosswalk, and people cycling would be required to stop. So in April 2017, a construction or reconstruction of Pandora Avenue was completed. And approximately a little bit more than a year later, the Canadian Federation of the Blind filed a BC Human Rights Tribunal complaint, alleging that the floating bus stop discriminated against blind people. So they requested the installation of chicanes and maze gates. And then we were brought in to provide an expert opinion on the safety of the bicycle facility on Pandora, and to also look at the various crosswalks or floating island. So overall, our safety analysis concluded that changes made on Pandora Avenue significantly improved safety on the corridor. So the overall safety was improved. And there are many reasons, but some of them includes that vulnerable road users are now separated from motorists, and significantly narrower travel lanes tend to result in lower operating speeds. So we also did a review of the pedestrian crossings, and we analyzed the safety or also compliance with guidelines, see what was available at the time in terms of guidelines for the design and construction of these type of facilities. And we also analyzed the safety level of those specific facilities. So the constructed pedestrian crossing, that's kind of one of the conclusion of our analysis, was that they were in compliance with industry guidance. One of the major safety treatments is the raised crossing, as they provide pedestrian greater prominence as they cross the bicycle facility, and increase cyclist awareness of potential conflicts. There were discussion about the type of traffic control system used at the pedestrian crossing. So here it consisted of pedestrian crosswalk signs, higher level of control systems. So for example, overhead flashing beacons or traffic signals are generally implemented at locations where the risk of conflicts with motorists is high or higher. And our conclusion was that while not all conflict risk could be eliminated, the design on Pandora Avenue minimized the interactions between road users with high-speed differentials, which effectively mitigated conflict risk with the raised and marked crosswalk as the key conflict areas, and to create a condition where yielding behaviors between prudent users would be expected. So that was a conclusion that was provided in the form of a report, but also was in court too. I had to testify about that. And before we get into the evidence presented and the decision itself, it received a lot of this case received a lot of media attention, and the decision made by the judge is more nuanced than what some of the journalists led their readers to believe. And I'll describe or tell you why. So in this case, so the plaintiff in this case was a group of people with reduced visibility. There were a number of them that testified in court to describe their experience using these facilities. You see the quotes here. They come from the decision document that is publicly available if you're interested. And this is just a summary of what the judge understood from the evidence presented by the plaintiffs. So in summary, they indicated that, you know, with these facilities, they cannot see the cyclist and cannot hear them. So they can determine if the cyclists have stopped, and they can no longer independently and safely board the buses from the sidewalks. So that was really the main issue for them. So now the court decision on overall safety. Basically, the judge kind of recognized or he indicated in his decision that the overall safety was improved. And he found that the decision to place the Pandora bikeway on the north side of Pandora to be a sound decision. In terms of design guidance, and that's one that is quite interesting, the judge concluded that design complied with the guidance, but the issue was that our guides did not consider properly blind people. So this means that the judge did not accept the position that the safety of pedestrian was addressed by mitigating the pedestrian conflicts with raised and marked crosswalks, and that additional measures need to be installed to address the needs of people with reduced visibility. So that is also quite interesting. So in terms of accommodations, it's not necessarily simple, and those flashing beacons were installed on another bicycle facilities to see if it addressed the need of people with reduced visibility. People with reduced visibility did not like them, but the judge still said that there weren't really viable solutions at this time to address their needs, and indicated that they should be installed along the corridor. So this decision will have some implications, obviously, from the local perspective. So now the city will be required to install these flashing beacons at each crossing on the corridor. In terms of future facilities in BC, there may be hesitation to install floating bus stops in Victoria and other cities in BC. Complaints, there could be more complaints that could be filed about existing bus stops. Major implication on our design, the design guide that we use, so it may require some changes related to the people involved in the development of design guides, and that's changing. But maybe there's a conscious decision that has to be made where people with reduced visibility are involved in the early phases or through the process of developing these design guides. There may be some new ways of designing such facilities. This is one approach where you board the transit stop from the crosswalk at a controlled intersection. This could potentially address some of the issues. So definitely future facilities in Canada may be impacted based on this decision, and definitely there's some research on how to better accommodate people with reduced mobility that should be done. So that concludes my my presentation. Thank you.
Thanks, Alex. We have a few minutes for questions. Again, please put them in the Q&A box. Oh, we did have one come through in the chat. So are cyclists required to have a bell in Victoria?
I mean, it's a good question. The main issue is, or the feeling from the people that were blind is that cyclists wouldn't systematically stop at the crossing, a bell or not. They weren't complying with the traffic control system, or at least it was the perceived, it was their perception. So it really is the lack of compliance that was the issue.
Thanks, Alex. We'll move on to Mark's presentation, and if there are any questions for Alex, feel free to put them in the Q&A box, and we will try and answer them at the end of the session. And so our next presenter is Mark Wilson. And Mark, we'll get you to share your screen and pass things over to you.
Okay, can you see that all right, Jennifer?
Yeah, that looks good.
Great, okay. Thank you very much, Jennifer. I'll just go to the first slide here. Let's see if it's advancing okay. Oops, it's not. Hang on here. Not quite sure why the slide isn't going. There we go. Okay. Yes, hello, and thank you for the introduction, Jennifer. So I'm a member of a road safety advocacy group called GEMS, where it stands for Going the Extra Mile for Safety. And we've been advocating for a 2+1 road pilot project in Northern Ontario, here in Canada, since 2015. My role with the GEMS committee is to collect information on 2+1 roads and report to various groups. And this presentation is based on a fact-finding trip that I took to Sweden and Ireland, where I toured and experienced 2+1 roads and met many road safety experts and officials. My report is entitled 2+1 Roads, Swedish Innovation, Canadian Railroad Solution. I'm sure everybody is familiar with Vision Zero, who's online today. And it plays an important role in the development of 2+1 roads. So this innovative Swedish program, established in the late 90s, follows the principle that humans make mistakes, and that in every situation that a human may fail, the road system should not. So 2+1 roads were a result of Vision Zero principles and have been the most significant reason for the reduction in fatal and serious injury crashes caused by high energy crossover and head-on collisions. Ireland, among other countries, followed Sweden's lead with their own successful 2+1 pilot projects. Before looking at the 2+1 road design, I just want to talk a little bit about some of the results of these roads. This slide is from a study referenced in my report, which compared Sweden's rural highways before and after 2+1 conversion. The application of 2+1 roads resulted in the study in a 79% decrease in fatal crashes for vehicles and an estimated 40 to 50% reduction in fatalities for motorcycles. This next study, a 2015 study, compared the relative risk of dying on various road types in Sweden. And you can see that 2+1 roads compare very favorably to 4-lane divided highways or motorways. We also see much higher risk on 2-lane rural roads, which is common around the world, certainly across Canada, because of the high levels of high energy crossover collisions. We can also see by this graphic that Sweden is a leader in road safety, thanks to Vision Zero and their use of safe system design to make their roads safer. And certainly we think we can do the same here. This also compares Northern Ontario and why our group has been advocating for the 2+1 pilot project. We continue to experience fatal head-on crashes on a regular basis on our northern highways. So let's look at 2+1 roads in a little more detail. This photo shows a 13 road in Sweden before being converted to a 2+1 road. The two travel lanes in the center are 3.5 meters wide with 3-meter shoulders, paved shoulders. These were the roads that had high rates of fatal and serious collisions. And Sweden wanted to set out to change these unacceptable statistics, but also wanted to do it in an economically responsible way. So they developed a system to transform these 13-meter roads to 13-meter 2-lane roads to a 2+1 profile while using the same platform. So this picture is one of the same location after the conversion. So you can see here with two 3.25 meter lanes on the 2-lane side and one 3.5 meter lane on the other. And they're separated by a 1.5 meter median reserve, which contains a crash rated physical barrier. So in this case, it's a wire rope barrier. And you'll notice that the shoulder has been drastically reduced, but this has not been a major problem in Sweden. The 2+1 profile alternates on a continuous basis every 1 to 3 kilometers, which allows each direction of traffic many opportunities for overtaking slower vehicles. The general goal is to allow passing opportunities for approximately 40% of a driver's journey. In some cases, the profile may be a 1+1 profile where the terrain is difficult, such as areas where there are rock outcrops, and significant blasting would be required to make room for an extra lane. Sweden has been building 2+1 roads with volume capacities between 2,018 to 20,000 average annual daily traffic. And in the last number of years, they've also started converting many of their smaller 9-meter 2-lane roads to a 2+1 profile, which requires some minor widening of the road platforms in some of the locations. The speed and performance has also been studied in various reports that are referenced because 2+1 roads have been around for a while now. And generally 2+1 roads have seen slight speed increases over their 13-meter roads. And most of these increases are on the 2-lane passing sections. Posted speeds are 100 kilometers in most situations. And the traffic performance is very good, up to approximately 1,500 vehicles per hour. There's been various barrier types used on 2+1 roads. And this picture I took in southern Sweden of a wire rope barrier that sits in the 1.5 meter median reserve. And this one is a version which crosses from side to side on the posts. And also note the rumble strip on either side of the median reserve, which warns the drivers should they get a little bit too close to it. Here is another 3-wire wire rope barrier, just a different design. It's an inline style with the cable sitting in the middle of the posts, and these posts bend when there is an impact, and the cable holds the vehicle from crossing over and having a high energy collision. Here's a photo I took in Ireland, and you'll notice the same style of cable barrier in this particular case. And also note the slightly wider profile, slightly bigger shoulders, on these Irish carriageways. And in Ireland, some of the 2+1 roads became unsuitable for the volume of traffic. And so they were able to expand the 2+1 profile to a 2+2 profile quite easily. And they've had success with these 2+2 roads with narrow medians, and they continue to build more. This photo is from a construction project I visited in Sweden, and you'll note the use of a semi-rigid steel barrier in this case. So this is different technology than the cable barrier, obviously, and now it is the standard barrier type used in Sweden and Ireland and other countries. And the primary reason for this change is the significant reduction in maintenance costs and the ability for these barriers to resist minor hits more effectively. This is a photo from Finland, and this profile is somewhat wider. Notice the wider shoulders, and also note the use of the semi-rigid steel barrier as well. So again, a little wider profile in this particular situation. 2+1 roads can be built at a fraction of the cost of a 4-lane divided highway because they're built on existing road platforms. And there can also be significant cost reductions by using at-grade junctions rather than costly grade-separated intersections or interchanges. So here you see a picture of an at-grade intersection with a left turn lane, and the barrier continues on either side of the intersection. Maintenance operations involve the use of TMAs for worker protection, and most maintenance operations are performed on the 2-lane side, as you can see here. From the photo that was taken off of my dash cam. I apologize for the poor quality of that one, but it's a good representation of some of the maintenance operations. This photo was from my winter trip to Sweden near the Arctic Circle, and with the wide wing effectively removes snow from both the single lane and double lane sections. And in some cases, they'll use 2 plows for tandem operation. I also spoke with representatives of the trucking industry, and they support 2+1 roads because their drivers are safer because of them. And there are also many locations built into the system for heavy goods vehicles to safely pull off the highway, as you can see here in this photo. When we look at emergency response, a reduction in serious and fatal crashes. So there's reduced call for response to fatal crashes, obviously. And when there is a response to emergencies, it's generally made from the 2-lane side, but not always. In some cases, roads have to be closed, just as they are here in certain situations. But there's generally been a very positive response from Swedish and Irish emergency services. So just to summarize some of the key points of 2+1 roads is, ultimately their safety results are equivalent to divided highways, but they can be built at a much lower cost and a much lower environmental cost. Their design is flexible to the terrain. So for example, where the terrain is difficult, they can be designed as a 1+1 for a period of a certain length. And if there needs to be expansion, there can be, of course, the 2+2 model, as the Irish have done. They're very effective on rural road networks. They are nice to drive. I like to call them sort of a lesson every time you drive, because when somebody wants to pass and when they shouldn't, obviously they can't. So it reduces inappropriate passing. It's a very self-explaining road, and they continue to be built around the world. Australia and New Zealand have used them quite extensively and with some success, with a lot of success. And we are beginning to see the use of median barriers in narrow medians in Canada. And this photo is one I took while visiting with the Ministry of Transport in Quebec near Gatineau. And this 6-kilometer section opened in 2020 and is primarily a 1+1 profile with a very small section of 2+1. And they've been very happy with the results so far. And lastly, the Ontario government has committed to a 2+1 pilot project here in Ontario. And we would like to thank the Ministry of Transportation for this announcement. And I'm a member of a working group along with Ministry of Transportation representatives working on a location selection process with announcement expected soon. And so that is my presentation. And if there are any questions, I'd be glad to take them.
Thank you, Mark. So any questions, feel free to pop them into the Q&A box at the bottom of the screen. So we have one that came in. So what was the main source of hesitancy to pilot the narrow median bearers?
The 2+1 road hasn't been a common application. In fact, there really aren't. The project I showed you in Quebec is really the first application of it in North America, for that matter. I mean, we have, in a sense, 2+1 roads on some of our highways right across the country where we have passing lanes. Except we don't have the median barrier and we don't have the separation. The 1.5.
Oh, great, that's going.
Whoops. And so one of the
okay. Yeah.
Oops, somebody else.
Oh, I think someone is not on mute, so if everyone could mute their mic besides Mark, that would be great.
Okay, sorry, Jennifer. Yeah. Okay, so one of the other concerns, of course, was the barrier deflection. You know, the barriers, there's some discussion about the fact that if a vehicle hits that barrier, it's going to deflect into the oncoming lane. Well, a couple of points there. One is, of course, if it crosses over and deflects into the oncoming lane, if the barrier wasn't there, they would hit the vehicle and we'd have a fatal crash. The other factor is when we test barriers, we use either in Europe, it's the EN 1317 standard, and in Canada, we use the MASH standard. And those standards are strictly that, testing standards, and they're tested at certain angles. And so when vehicles hit the barrier in reality, they hit at a much lower angle than a lot of that testing. So that's been the experience in Sweden and Ireland and Australia, where the deflection into the oncoming lane just doesn't happen, even though that has been a major concern. So I would say that's one of the hesitancy factors associated with it. Yeah.
Okay, so a couple more questions. What do motorcyclists think about these median barriers?
Yeah, as I mentioned in one of the stats, you know, in all cases, Australia did a large study on this as well, because there's a very significant use of motorcycles there. And they found that the reduction in fatalities for motorcyclists was reduced. I mean, anytime you're on a motorcycle, you're at risk to any barrier, whether it's a roadside barrier or you know, something outside of the clear zone. However, I showed the semi-rigid steel barrier, that the one from Sweden, and there's definitely some more acceptance of that particular style of barrier as opposed to the wire rope barrier. But as I said, all the statistics, all the studies show that motorcyclists are safer on these 2+1 roads than if they didn't. And one of the reasons being, of course, that there aren't crossover collisions of vehicles that are coming across and hitting them.
Great, and we'll take one more question. So are the barriers easy to see at night? So from your pictures, it looks like they have deflectors, but I can imagine it would be harder for large trucks to see them at night.
No, they're quite well lit with reflectors. When I drove in Sweden in the winter, it was actually very nice having that barrier down the middle. Compared to driving in Northern Ontario in the winter, you have really nice delineation, and the barrier provides a really helpful delineator down the middle and helps you know where you are. Even in, you know, in of course Northern Sweden, there's very, very, very little light in December, so it's almost always night. So the reflectors are very effective.
Excellent, thanks, Mark. And so we'll move on to our final speaker for the session, which is Tate Hupkareo. And so Tate, if you want to share your screen, and I'll pass it over to you.
Perfect. Thank you, everyone. First, I would just like to take this opportunity to acknowledge the traditional territories of the people of the Treaty 7 region of Southern Alberta, Canada, which includes the Blackfoot Confederacy, comprising the Siksika, Piikani, and the Kainai First Nations, as well as the Tsuut'ina First Nation in Southern Dakota, which includes the Chiniki, Bearspaw, and Wesley First Nations. The city of Calgary is also home to the Métis Nation Alberta Region 3. So, as I'm sure many of you are aware, active transportation, including walking and bicycling, can greatly improve the physical and mental health of individuals while reducing the risk of cardiovascular diseases. Further, it can have indirect influences on our environment as a whole. Unfortunately, the proportion of children using active transportation in school has decreased substantially over the last few decades, while travel by motor vehicle has increased. So this may have increased both the actual and perceived risk of injury to children during active transportation. And in Canada, motor vehicle collisions are the leading cause of injuries for children using active transportation, with some reports saying over 70 children being killed every single year. In Alberta alone, over 400 emergency room visits occur each year from children due to bicycling or pedestrian injury. So while there are many risk factors for pedestrian and bicyclist motor vehicle collisions, as we've seen, talked a lot about today, speed is predominant. Not only does an increase in vehicle speed increase the probability a collision will occur, it can also increase the likelihood that a collision will result in death. So this commonly is represented as a sigmoidal relationship, resulting in graphics such as the one on the right by the ITE. And this risk can also influence parental perspectives of safety, so potentially reducing the number of children allowed to use active transportation mode to get to school, which can potentially further reduce the safety and health benefits that can come with active transportation. And so in order to reduce the risk of pedestrian and bicyclist death on our streets, we need to find effective ways to reduce the speed of these vehicles, specifically at locations where we have higher child activity, such as around schools. So this research study that I led sought, in collaboration with the City of Calgary and funded through the CIHR Health System Impact Fellowship Program, sought to use a step wedge randomized trial design to evaluate the effectiveness of two traffic calming measures by reducing speed volume while increasing active transportation around elementary schools in Calgary. We also sought to evaluate how these interventions influence parental perspectives of safety by having parents at these schools complete a survey both before and after installation of these traffic calming measures. So out of the 364 public schools in Calgary, we excluded those that had higher grades or special programs, any that did not have an intersection within 100 meters of the main entrance, or had different studies going on looking at their active transportation or speed. Of the 109 eligible schools, we randomly selected 52 to receive an intervention during a specific week within our study period. So we had two interventions. The one on the left, the in-street pedestrian sign, and the one on the right, the traffic calming curb. So these installations were completed by either the City of Calgary or a contracted company, according to City of Calgary guidelines. So the in-street signs were bolted into the road along the median line, 1 meter behind the crosswalk. They do have a flexible base, so if they do get hit by a motor vehicle, they'll just kind of bend over and then pop back up. So they're really pretty resilient that way. The traffic calming curbs are preformed cement placed beside the curb to narrow the street right before the crosswalk. So depending on the road geometry and size, between 1 and 3 curbs were usually used to narrow the road at that place. And both interventions can either be temporary or be left in place for an extended period of time. And just for context, speed limits at all Calgary schools during this study period, they're set at 30 kilometers per hour between 7:30 a.m. and 9 p.m. And then between 9 p.m. and 7:30 a.m., they're at 50 kilometers an hour. So after selection, schools were ordered to receive their intervention during a specific week within the study period, while ensuring equal number of schools in both the north and south sides of the city. And that was done for logistical purposes. Each week, 8 schools would receive an intervention. So 4 were to receive the traffic calming curbs and 4 would receive the in-street pedestrian signs. Interventions were installed at the intersection closest to the main entrance of the school that we selected. So this is kind of the whole schedule of the study. We had our interventions, they started being installed in July 2020, and we finished in October 2020. So prior to the installations, the parental survey was sent to all parents at the participating schools in June, and then they did get their repeat post-installation survey in November of the same year. So in the schedule, the interventions, they were installed at the start of a specific week, and that week was shown in the blue box. The week prior to installation, we took traffic and active transportation data in the green box, and then we can repeat those same measures the week after installation, which is shown in the red. We did have a small gap in the study scheduled at the end of August, just to separate the schools that were in session in September and October from the schools that were not in session in July and August. So we didn't have any crossover of that data. And then at the end of each grouping, we did have some schools that we collected data for multiple weeks as well. So this schedule just allowed us to primarily compare the pre-intervention outcomes, their post-intervention outcomes at each school. So along the horizontal line, comparing the green box to the red box, but then also we're able to compare our post-intervention outcomes at one school compared to the pre-interventions outcomes at a different school during the same week. So that's the same as comparing a red box to a green box, but along a vertical column. So we can look at both kind of comparisons in this. So data was collected using a couple of different methods. We used the pneumatic tubes, which we mentioned earlier today, placed across the road, approximately 30 meters from the intervention. So that collected traffic speed and volume. We also collected active transportation counts via microvision video cameras, pointing at the crosswalk that we were looking at. Only 1 week of traffic speed and volume data was collected before and after, and then only 1 day of active transportation data before and after as well, just due to logistical and financial limitations of the study. And then for the surveys, we did have RedCap, so an online survey platform that was sent through email to all of the parents at the schools from the school administration. So just some really early results we found so far. So far what we've looked at, we've averaged all the schools across all the day, the entire day. We have seen that both the traffic calming curbs and the in-street signs have reduced traffic speed by an average of 1 kilometer per hour. Traffic volume, we saw some, at least so far, we've seen a little bit mixed results with having an average between vehicles increase at the traffic calming curbs while having a decrease about the same at the in-street signs. And for active transportation, we've seen actually a reduction in how many people we've counted at these locations before versus post. For the survey, we did receive over 1,200 responses, most of them being from the pre-intervention time period. Out of the 52 schools that were part of this, 47 actually participated in the survey as well. And so we had approximately average 27 surveys per school. We don't have any data yet, haven't been able to find that results from that specifically. So just some strengths and limitations of the studies overall. While the results so far are very early, we'll be able to have more soon. But the study design itself, I think, provides a unique ability to investigate the influence that these built environment interventions have on traffic and active transportation. It's not every day that we get to go use the opportunity to use this randomized controlled trials in our community in this way. And our partnership with the City of Calgary has definitely made that possible. The temporary nature of these features and these interventions, I think, is also really important. It really allowed us to go to more sites and as well look at features that traditionally may be more permanent, such as full curb extensions, whereas doing the full permanent version would be quite prohibitively expensive. And while this design does assist with the costs of data collection, so we're only looking at some sites every single week, so we don't have to collect all the data all the time. We did not have unlimited funds and resources. So unfortunately, we were unable to look at ongoing data collection every single week for a longer period of time. Further, the location of the interventions were determined by the official entrance of the school, which may not have been the more popular entrance. And then finally, as you may have noticed, all of this data was collected during the COVID-19 pandemic. So we need to keep that in consideration when looking at how the different traffic volumes and active transportation counts may have changed or how they may have compared to normal. So future steps, we do intend to conduct a full analysis of the data. So including investigating the influence of time, so different time periods of the day. So looking at school drop-off versus pickup time, nighttime versus day, as well as how the season progressed. We know that as we got closer to October, a little more snow happened at our schools, so that may have influenced how many people used active transportation. Further, we were able to actually go back in spring this year in 2021, so we will be able to look at longer term effects of these interventions. And then, as I mentioned, the data we collected were in school zones, which from 7:30 a.m. to 9 p.m. is 30 kilometers per hour. So a lot of these results may be generalizable more towards locations that have similar low speed limits. However, I do think that areas that have higher speed limits may actually see potentially greater changes in traffic and active transportation following these due to their potential safety impact on the environment. And finally, I think the success of the study showcases the effective partnership between the University of Calgary, the City of Calgary, facilitated by the CIHR Health System Impact Fellowship Program. So I think opportunities similar to this may be of interest to other municipalities, other research organizations, allowing similar study designs to evaluate other specific traffic safety interventions. So thank you to all my colleagues who helped make this happen, as well as my funders, and happy to answer any questions. Thank you.
Thanks so much. If there's any questions, again, feel free to pop them into the Q&A box. We do have a bit of time, so if you have any questions for any of the other presenters, I know there was one question we didn't get to related to Alex Nolay's presentation. I'm just going to make sure. Alex, are you there?
Yes, I am.
Okay, there was a question that came through around if enforcement of compliance was an option related to your study there.
Enforcement compliance. Yeah, I guess it's really difficult with cyclists to make sure to comply or make sure they give the right of way at those locations. It really is, I believe, an issue of design and proper design, and make sure that the key messages are there, so there's higher likelihood of them giving the right of way to pedestrians. So that's really, or maybe there's some education that will have to be done, teach or show cyclists how to use these types of facilities. They're relatively new, not many municipalities at them. So, but yeah.
Thanks, Alex. Any questions for Tate? Any final questions for any of the presenters from today's session? Or this afternoon session, I should say. don't see any coming through. So I guess maybe we can wrap up a little early if that's possible. Just want to thank all of our presenters from this session. Thank you so much for sharing the work that you're doing to keep our roads safe. And thank you to everyone who attended, and I hope you all enjoy the rest of the conference for the next couple days. And yeah, with that, I believe we can end. Thanks so much. In terms of a game code, I wasn't given one, so I'm gonna say no.